Johnny here with Simpson Math. In this video, we're going to continue to calculate volume of three-dimensional solids. In this lecture in particular, we're going to talk about the disk and washer method. Before I get into it, just a vocabulary term, the solid of revolution. So right here, I've got a circle, just this plain two-dimensional circle with radius r. And over here I have a line, and what I'm going to do is revolve that plane circle about that line. So I'm going to take that circle and I'm going to push it through the paper, and I'm going to revolve it around that line of revolution. So it should look something like this, passing through. So that circle goes into the paper, it revolves around the line, comes back up on the other side. I can see the circle again here, the flat circleness again here. But the circle just continues to revolve. It comes up off the paper and like so. All right. That shape, that plane circle being revolved around that line, creates what I want to call a donut, but that may be because I'm a Simpson and we Simpsons do like our donuts. But in math, we call that a ring torus. That shape of taking a plane circle and revolving it about a line, that's called a ring torus. So the ring torus is a solid of revolution. I'm going to be talking about solids of revolution today in this disk and washer lecture. And it's just this idea. We have a plane figure, but when we rotate it about some line, like the x or y axis, it's going to create this three-dimensional solid called a solid of revolution. All right. So let's just jump straight into an example. All right. We have considered the plane area as the area between the line y equals 1/2 x plus 1 and the x-axis on the interval 0, 12. That's just a line. I'm going to then rotate that area about the x-axis to create a solid of revolution. All right, let me just draw this line real quick. I have a ruler. I'm not sure why I'm not using it. Let's see. Something like that. Looks like I need to go all the way out to 12. Line 1/2 x plus 1. I start at the 1. 2, 3, 4, 5, 6, 7, 8. I think that's all I need to do. Now 12 though. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 will give me 7. If I plug in 1, I should get a fraction. So I'll plug in 2. Half of 2 is 1. I should get out 2. And I get this line. Along the interval 0 to 12, I've got this line 1/2 x plus 1. And I'm going to revolve that line about the x-axis. So I have a little symbol for that just to help us visualize how this solid of revolution is being formed. Just a little swirl on the x-axis with a little arrow so the reader can tell, oh yeah, that line is going into the paper, revolving about the x-axis, coming out of the paper, and then flattening back out. So it's creating a cone. Well, it's been cut off, looks like at the tip. All right, if 12, 7 is a point up there, then 12, negative 7 will be a point down here. I can put that little circle in there. Move back down to -1. I'm draw that same line, but when it's over here. And then I'm going to do my best to make a three-dimensional object here. I'm going to create those that revolution, so these circles. And hopefully y'all can see it's just a cone that the very tip has been chopped off. Alright, we've created a solid revolution, and my whole goal is to find the volume of that said solid. Now, I claim we already know how to do this. In the previous lecture, we were talking about volume by slicing. I think I've already shown some slicing we could do. I could take this circle, because notice these cross sections, when I do the revolving, it's just going to create circle cross sections. And if I do this perpendicular to the x-axis, then I'm just slicing these with respect to x. Oh, and in order to do volume by slicing, I need the area of the cross section. Well, here we're talking about the area of a circle, pi r squared. So this is fallen into like the groove of things. I know exactly what I'm supposed to do. Let me just say some stuff here. I see cross sections that are perpendicular to x. That is, we're given x just a little bit of width. That is, I need an area formula of a cross section with respect to x. Okay. Well, the area of a circle is pi r squared. So I just need the radius. Well, the radius of these circles is always going to be the distance from the x-axis up to that function right there, and that function is 1/2 x plus 1. Over here, the radius of this circle that I drew, that radius is that line, 1/2 x plus 1. Over here, the radius at 2 is just going to be 1/2 x plus 1. Start off, it's going to be 1/2 is 0 plus 1. It starts off at 1, the radius of 1. It ends with a radius of 7. But the radius itself is just that function f of x. So I'm simply going to square my function. Now notice I have written above me a disk method formula, because this is going to be the same thing over and over again. If I take a function and revolve it around a line, they will always have these circle cross sections. So it's always going to be the case that we're trying to integrate pi r squared. And it's always going to be the case that the radius is just going to be that function. All right. So I claim I've got the area of a circle, my cross section, is pi times my radius, which is 1/2 x plus 1 squared. And we know that in order to calculate the volume, we can integrate that cross section along the interval 0 to 12. With respect to x. Now the formula is not a fail-safe. This is working out nicely because I am revolving about the x-axis, so it's creating those perpendicular to the x-axis cross-sections. But if I were to revolve about the y-axis, you can see that it's going to be very similar, still creating circles. You're just going with respect to y instead of x. And so the f of x notation may not be true if you're talking about something that's not a function, I suppose. or if it's written in terms of y. But it's the same idea. The volume using the disk method is always going to be pi times the radius squared. Okay, this problem is now, the hard part's over, and I'm just going to integrate it. So I can do that real quick. Pulled the pi out of the integration process. I guess I can square that out. That might make the integration easier. I'll have to write that down twice so I can do the distribution. So it's a quarter x squared plus a half of x plus a half of x. I think that's plus x. And then 1 times 1 is 1 squared. Or 1. So I've not integrated yet. I'm just going to rewrite. I'm just going to square out the radius. And polynomials are really easy to integrate, so I'm just going to do so. All right, now I can integrate each of these independently. I'm just raising the power by 1 and multiplying out front by the reciprocal of the new power. So this becomes x cubed, the 1/12 out front, plus 1/2 x squared plus x. And I'm going from 0 to 12. Oh, the 0 is super nice. That's going to destroy everything. So really I just need to plug in a 12. Oh my gosh. 12 to the 3rd power. I don't think I can do that in my head. Oh, but that's going to be, I can kick it down. Never mind. If I reduce one of the 12s, then 12 times 12 is 144. I can do that. 144 cut in half is 72. So far, so good. That looks like 5, 6, 7, 8, 7, 8, 9, 10, 11, 12. That's going to be 228 pi. That's the volume of that solid of revolution. I claim this is simple because we already know what we're doing. I took a line, I revolved it about the x-axis. It created this 3-dimensional object with circular cross sections, and we could just basically apply the volume by slicing technique. These are creating disks, just solid circles, a disk. Volume pi r squared. Let's do it again. Maybe if I do it with respect to y, maybe something changes. I don't know. Okay. For this next example, R is the region bound by y equals 2 minus 2x, so another line, y equals 0, so the x-axis, and x equals 0, so the y-axis. So probably quadrant 1 is what we're talking about. Compute the volume of the solid generated by revolving that region about the y-axis. Okay, step 1, just get a picture of this region so we can talk about it. This is a line, starts at 2, and it has a slope of -2. I think I'm going to zoom out on my axes if I can. That is, I'm going to let every 2 of these lines be 1. That line crosses the y-axis at 2. And then I go down 2 over 2. I'm sorry. Let me see. If I plug in 1, 2 minus 2 is, oh, it cuts off faster than I thought. Oh yeah, slope of 2. Alright, slope of negative 2 down to over 1. Yeah, I'm glad I zoomed in because I'm done now. That's it. Guess I'll just leave this. So the region formed by the x-axis and the y-axis and this line looks something like this. This time I'm going to revolve it about the y-axis. So I'll draw my little line something like this. So let the reader know I'm revolving about the y-axis. Maybe I can use some color here to help showcase what this is going to look like. And again, we're getting another cone, this time a complete cone. Well, half of a cone, I suppose. And again, I hope you see the circular cross sections. So if I needed the area of that circle, well, that's just going to be pi r squared. And the radius this time is the distance from the y-axis out to this line. Let's see. This equation is solved in terms of x. For a of y, I really need to solve this in terms of y. So I need to solve this for x. I think to do that, I will add the 2x over and subtract the y. And then I will divide everything by 2. That is the x distance here. That's the radius of these little cross sections. Alright, so a of y is pi times that being squared. But I want the volume, so I'm going to just shove it into this formula, but it's the same idea. The volume just takes this area function and it's going to sum up all of them along the interval I'm talking about with respect to y, so from 0 to 2. Pi, which comes out of the integration process, times r squared. And this is with respect to y because my cross sections are perpendicular to the y-axis. I'm stacking these coins instead of lining them up. Okay, like before, I think I will expand this out. To me, it's easier to integrate. And I like to write it down side by side so I don't make any mistakes. 1 times 1 is 1. I have a negative 1/2 y and another negative 1/2 y, so I should have a negative y. Very similar. This becomes a positive 1/4 y squared. At this point, the hard part is over. Now this is just plug and chug and some trivial stuff, but I can do it real quick. Thank you, Mr. Simpson, for continuing to give me these zeros. Makes the calculations easy. Let's see. 2 cubed is 8. 2 squared is 4. There's a minus 0 in there, but it kills off all those y's. All right, then that is just 2/3. That is -2 and +2. Oh, those cancel. Oh, so I get 2 pi thirds as the volume of this cone. Okay, that is the disk method. Whatever function I give you, I don't know, whatever it is. If I have you revolve that around an axis, it's going to create circular cross sections. And in order to calculate that volume, we just find the area of those cross sections, circle, pi r squared, and we integrate it along the interval. Perfect. All right, nothing new. What may be kind of new is the washer method, but still I claim you know this as well. Let me show you what I mean by a washer. Okay, I've got some Cartesian plane with two functions defined over the intervals 0 to a, looks like. And I'm going to revolve it around the x-axis. And because I anticipate I'm probably going to erase a lot, I kind of drew it over here to help me figure this out. All right, but there's my plane area, and I'm going to revolve it about the x-axis. So the line that kind of curves up will now kind of curve down. The line that grows up will just grow down. So I've got that same shape just been reflected. And I'm going to use that to create little circles to help me see the solid of revolution. So I'm using the g of x to create little circles. And then I'm going to create the f of x's to create these bigger circles. It may be kind of hard to see, especially since I'm not the best drawer, artist. But we've got it's another, or this is that ring torus. I've got basically a donut sitting here. Looks just like that. Or I'm envisioning, for whatever reason, like a Star Wars, when those airplanes are always having to like fly within an asteroid or something. Something like that. There's a hole in the middle of that donut. Alright, so here we have a solid of revolution. This is a ring torus. And I need to find the volume. Okay, well, I see circular cross sections yet once more. I see area from the x-axis to g, and I see area from the x-axis to f. Okay, let me get some color in here and maybe it might help. This pink thing that I just grew is that pink thing I just drew. This pink is the radius of the circle cross sections when we rotate g. Pink is the area under the g function and between the x-axis. Okay. Blue is the same thing but f. If I were to rotate only f, forgetting g, if I were to rotate f about the x-axis and use the disk method, that would calculate all of the volume under f, like rotating f. Pink would be just rotating the g. But in this case, I don't want F and I don't want G. I want the area or the region that's formed between F and G. So that should sound very familiar to you. Between. If I were calculating area between two curves, how would I calculate that orange area? Well, I would take the area of F, the bigger area, and subtract the smaller area, pink. I'm going to do the same thing with these solids of revolution. I'm going to calculate the volume of the blue solid of revolution. Then I'm going to calculate the pink solid of revolution. And then I'm going to subtract. Blue minus pink will give me orange. Okay, I've got it kind of written above me. If I want to find the volume of a washer, so a washer is just a disc with a hole in it. So if you've ever hammered nails, there's discs and there's washers. The washer has that hole in it. All right, that's the same idea. I take the top function minus the bottom function, and I'm treating them as radii. So I'm squaring the top function and I'm squaring the bottom function. I'm going to write that down just because I need to write it 5 more times. Pi from some interval, that's a different a than I'm using here, like 0 to a or 1 to 12, I don't know, of the top function, and we know that that alone means different things. That could mean rightmost. If I'm looking at this with respect to y, it could mean the highest. If I'm talking about with respect to x, minus the low function squared pi r squared. All right, let me jump into an example, and it'll make some sense, I'm sure. I promise. Looks like I've done it. I used pink, orange, and blue. Not on purpose. All right, let's do. We've got a region bound by y equals x and y equals the fourth root of x. And we're going to revolve that about the, oh, I have it over here. Sorry. R is the region bound by the identity function y equals x and the fourth root of x. I'm going to compute the volume of that solid generated by revolving that region about the x-axis. Okay, sounds good. First things first, I need to get a picture of this region. Fourth root of x is a very tiny teapot arm. So let me try to zoom in again. I know the parent linear, that's easy to do. Now the fourth root of x, I don't know that many numbers. The fourth root of 0 is 0. Okay, good. The fourth root of 1 is 1. Okay, that's good. So yeah, it's in this region right here. The fourth root of 2. Okay, so this thing kind of grows really fast, and then it kind of curves in here. all I really care about is that region bounded by those two curves. This is a little bitty plane area, this slice in here. I'm going to take that region and I'm going to revolve it about the x-axis. I'm going to draw little circles to help me visualize that three-dimensional object. I still can't envision it. Let's see. Oh, it is a washer because it's not flush with the x-axis. So there are these there's a hole in here as well. Well, me starting off. That's no good. And the endpoints are not really helpful. It's that middle part that was better. Maybe I used the top function last time, blue. I'm going to use pink for the smaller. And then orange is just that area there. Okay, so I can't really envision that thing. It somehow comes to a point, but then it curves around like a nice bowl, but it would be like it would topple. And then it does have a hole in there. I don't quite understand it, but it does go around. It's a bowl. It's a bowl that comes to a point. Yeah. Okay. And it's easy. Circle cross sections, perpendicular to the x-axis. Volume is pi r squared. It's just that my radii is not one radius. I've got two. So when I take a look at this torus in here, I'm taking the top one, so the blue one, minus the pink one, and that's going to give me what I'm after, the orange. So I just need to know my top function and my bottom function. Well, that's obvious. My top function is the fourth root of x. My bottom function is the line. So to set this thing up, I'm going to calculate the volume by integrating with respect to x. So from 0 to 1, pi r squared. I'm going to pull the pi out of there, and then it's r squared. But my r is going to be a top r minus a bottom r. So the top radii is the blue function, which is the fourth root of x being squared, my radius squared, minus my bottom radii, x squared. That's going to give us the orange leftover stuff that I'm actually after. Okay, let me square fourth root. That just becomes a square root. Or x to the 1/2 power. Polynomials are nice and easy to integrate. I am continually thankful for that 0 every single time. All I have to do is plug in a 1. This is just arithmetic now. I'm done with the calculus. Square root of 1 cubed is still 1. So I've got 2/3 minus 1/3, which is 1/3 pi, or pi thirds. That is the volume of taking that plane and revolving it about the x-axis. That plane is going to create a solid of revolution. it would be a ring torus. I don't know about that coming to a point, how that affects the definition. But it's that it creates that three-dimensional object, and the volume of that object is pi-thirds. All right, go do the homework. Do your best to draw these images. We're going to kind of need to practice this skill as we move on. So now's a good time to practice.